Hi everyone. So in this lecture we are going to learn about a new type of virtualization called OS level virtualization. So far we have learned about system virtual machines and process virtual machines. And OS level virtualization represents another more lightweight kind of virtualization that aims to provide isolation, but at the same time it tries to maintain the performance of applications running within uh, virtualized units. These virtualized units are also commonly known as containers, although that name itself has come to mean different things over the recent years. So we will, when we say containers, we are in this lecture we are specifically referring to OS level virtualization. But keep in mind that containers may also mean uh, some other types of virtualization in different contexts. All right. So let's first look at the notion of isolation. What we mean by isolation. So isolation means that you take a process or a group of processes and then you limit the view of the world seen by those processes. So this could mean that we limit the amount of system resources that these processes use, or which other processes they can see or talk to, or whether they can access the network, which other machines they can talk to, and so forth. Uh, so there are, so far as I mentioned, we have seen two extremes. There are traditional processes that have a virtual address space uh, and they're scheduled and managed by the operating system. And then there are virtual machines which have their own operating system and all the applications running and managed within the operating system. So uh, we take a look at each of these individual extremes. Traditional processes, they get their own virtual memory. Every process, if it is single threaded, then it would think that it has its own virtual CPU. If it is multi-threaded, then it thinks it has many virtual CPUs. And then they access privileged services through system calls. So they make system calls to the operating system. The operating system itself is shared across these many processes, and then the OS executes those system calls on behalf of the processes. Right. So this is kind of, it looks like each process has some isolation, but then different processes can also see each other within limits, meaning that you can get a list of other processes running in the system. You can set up inter-process communication or shared memory. You can send signals to other processes, so long as user permissions allow such activity. You can also access files. You can see the structure of the file system. You can set up network connections and access I/O devices like keyboard or mouse and so forth. So, although the process have certain level of isolation, there is also a lot of visibility across all system-wide resources. More importantly, if any single process gets compromised, then that process in turn, compromises the host operating system, then all the processes within the machine get compromised. They're all vulnerable. So traditional processes don't provide great isolation. There's some isolation, but not a whole lot, right? System virtual machines, on the other hand, they uh, try to provide stronger isolation, meaning that you take a group of processes that trust each other and you pack them together into a box called a virtual machine and provide that virtual machine with its own operating system. And everything that happens within a system virtual machine stays within that system virtual machine. So this way, process within one VM cannot see process in the other VM. They cannot manipulate the process. They can't send signals. They can't set up inter-process communication. You can set up network communication between processes in across two VMs, but that's almost like talking to another machine, another process on another machine, right? And these so VMs are managed by a hypervisor layer, whose primary goal is to maintain this isolation, right? So again, just like with processes, system VMs, each one gets its own guest physical memory, or a virtualized view of the physical memory seen by the guest OS, and it gets one or more virtual CPUs that look like real CPUs to the guest OS. Okay, and then it may also get virtual I/O devices like virtual disk, virtual network, and so on. So the level of abstraction exposed to a system virtual machine is more closer to the machine. It is ISA virtualization, right? Um, so, so this is a very strong form of virtualization, but it comes at a cost, which is that every system VM needs to have its own operating system. Okay, and then any privileged activity by the operating system, guest OS, it is emulated by the hypervisor. So there's a performance cost as well. So processes, they share too much, and you get great performance, but they are not isolated enough. System VMs provide great isolation, but there is significant performance cost, and as well as memory utilization cost. So with operating system level virtualization, which we are considering here, we want to combine the benefits of both, sort of, right? So we want isolation of system VMs and performance of regular processes. So how do we do that? So the key idea is that you take group of processes and bunch them together so they see a view of the world that and nothing else. So so in this slide, we're kind of putting all these options together side by side. We have seen traditional system virtual machines. We have seen traditional processes. So containers or OS level virtualization, it takes groups of processes, packs them together in a container, and all the processes within a container can see each other, talk to each other, do all the regular things, but they see nothing outside the container. Okay. So we're going to get more specific about what it means to see nothing outside the container. Like, what is this view of the world that we are trying to restrict? So containers, they are groups of traditional processes. And OS level virtualization mechanism will restrict the resources accessed by each group of processes. In Linux specifically, this a container consists of two major components. One is called namespaces, which refers to the set of resources that a group of processes can name and access, and the other is control groups, which is the how much resources a group of processes can access, like how much CPU or how much memory, and so on. So let's take a look at namespaces first, and then we'll go to control groups. So namespace basically refers to the idea that if you cannot name something, then it doesn't exist for you, right? Okay, so if something exists, then you use a name to access it. For example, with virtual memory, so you can use virtual addresses to access any byte that belongs to a process, and that's in the memory of a process, right? So virtual addresses are then translated to physical addresses by page table and the MMU. And if there is a physical address that doesn't belong, that's not mapped into the virtual address, then the process can't access those physical addresses. Why? Because it can't name them. Uh, so you can take this idea further and you can apply it to other resources. So the earliest example of applying namespaces to file system was the Chroot mechanism, or change root as it's called. And this was not really meant as a namespace isolation mechanism, but system administrators would use this Chroot mechanism to for system maintenance. For example, you might get a hard disk that needs some maintenance, like you want to do file system check or formatting, or you want to change configurations. So you mount this hard disk onto an existing machine which already has its own hard disk and its own file system. Okay, but then you want to operate on this new hard disk which has this file system that needs to be maintained. So what you can do is you can chroot into the mount point where this new hard disk is mounted, and then that shell environment where you're working, it would pretend that the root starts from the mount point of the new hard disk. So any commands that you execute, it would look like you're executing on the root as a root on a regular Unix system, but then because you're rooted into this new mount point, as a result you will be working in a restricted environment. So this did not provide any security or isolation as such, because there were lots of ways to bypass the path name restrictions imposed by chroot. But then over time, people kind of started relying on chroot for security without really understanding its implications, and then it led to a lot of problems where there were security breaches. Uh, so this of course gave computer scientists an idea that you could take chroot and then make it something that actually gives you security. So an earliest example was this FreeBSD jail mechanism, where they took this chroot idea and then they applied it to many other system resources. So you would run a process or an application within a jail, and the jail would place restrictions on what it could do. So you could, for example, put restrictions on which parts of the file system the jail process can access, which you can kind of create a set of users, including a root account within the jail. You can put restrictions on network communication, network identity. Like a jail process can have its own network identity, and it can't touch other processes or communicate with them. So jail was meant to protect the rest of the system from the jail process. It's not trying to protect the jail process, rather it is protecting the rest of the system from the jail process. So this is important to understand what's being isolated. Okay, so jail process is not being isolated, rather the rest of the system is being isolated. So, but then people found that again, their jail escapes were possible, meaning that there were certain vulnerabilities in certain system interfaces that people could exploit to access system resources outside the jail. All right. So it's kind of a cat and mouse game that security researchers play all the time. Okay. Uh, but the basic concept was right, that you could extend namespaces to other system resources besides just memory or file system. So the concept had been around, and then Solaris had its own version, Solaris operating system, Solaris zones, and then Linux came up with Linux namespaces. This was kind of late in the game, but finally they had this idea of namespaces in Linux implemented. And if you check the man page of namespace, it gives you the following very fairly accurate definition of a namespace. It is that a namespace wraps a global system resource in an abstraction that makes it appear to the processes within the namespace that they live in their own isolated instance of the global resource. Okay, so what it says is you can take a resource like, let's say, process ID, and then for a group of processes within a namespace, process ID namespace, they will look like they have their own process ID space, that their own root, their own init, and their own systemd and all that stuff. But then this process ID namespace is really part of a bigger namespace that's outside of the namespace, and that these processes cannot see. So that's one example. And then you can similarly create an IPC namespace, the namespace of processes with whom you're allowed to communicate, or a file system namespace, which is the portion of the file system that a given set of processes can access. Network namespace, that is assigning your own virtual network ID, MAC address, IP address, and so on. And user namespace, it refers to user ID, or group IDs. Okay. Uh, so from this discussion so far, at least it should be clear that that these are not namespaces don't really physically isolate the resources, but then they make it appear to the group of processes that other resources are not accessible. Now, in Linux, the other component of when you create a container, there are two components, as I mentioned: namespaces and control groups. Control groups are Cgroups. So besides just providing namespaces, control groups keep track of how much resources a group of processes are using. So using control groups, you can restrict how much CPU a group of processes can use. You can limit network bandwidth, the amount of memory, and so on. So if you use namespace and cgroup together, you can kind of create a jail-like environment where you're restricting various capabilities of a group of processes. Okay, so these two together are known as, or at least originally in Linux, these namespace and cgroups together were known as containers. But then, there were just so many parameters to manage and configure when you create a container that more sophisticated packages like Dockers and LXC and now LXD and so forth, and so all these started emerging with their own tool stack. A big part of a container namespace is the file system. Now every container wants to have its own distribution image, like you can have a Ubuntu container, or some other Linux distribution container, and then with its own set of application packages. So what over time happened is that containers became more associated with packaging the file system part of it, and once you have a file system, a specific distribution of packages, then you can then put them inside a namespace and control group and then fire them up, and it gives you the execution environment you want. And as I mentioned, the term container itself has come to mean different things. What I meant was that now, instead of just referring to namespaces plus control groups, sometimes people also take these container images, which is essentially a file system package, right? And then they run it inside a virtual machine. So and which is then controlled by a Docker, so like a system virtual machine. So now you're really using a system virtual machine with a Docker like tool, and then though you're calling the whole thing still a container, which is okay. It's just an evolution of terminology, but just something you need to be aware of as computer scientists, that when we say containers, what are we referring to? Is it traditional namespace with cgroup, or is it uh, a something that looks like a container but runs inside a system VM? And finally, I want to end this talk with the idea of a single system image. So so far we have been talking about taking all the process within a single machine, and then we group some process into smaller containers, right? It's like breaking apart a single machine into smaller machines. But single system image goes in the other direction. It says that let's say you have many physical machines. How can you make them look like they are a single machine with a single namespace? So single process ID namespace, single network namespace, single user ID namespace, and single memory, and so on. So those are single system images, gluing together many machines and making them look like one. So there have been, again, this is not a new idea. It's been there for at least a couple of decades, if not longer. And there have been various projects like Mosix, OpenSSI, Carry Guide, and so on that have tried to create single system images. Mosix, for example, had quite good commercial success as well till virtual machines came along. So again, we are taking the idea of namespaces and extending it across the boundaries of a physical machine. And one big component of a single system image here is the ability to do process migration, where you want to be able to move processes from one machine to another machine and still let it remain as part of this larger single system image ecosystem, right? So So that's all I have. Again, feel free to research this topic. Feel free to ask me questions. This is a very emerging field with a lot of changing terminologies, but also changing meaning to existing terminologies. So sometimes it's hard to keep up with all these terminologies, but this is a good place to start.